what I'll try to talk about right now is how can we achieve that, and the facilities that are required, or the facilities that are available right now for you to apply those regimens that you'll be discussing over the past couple of days, or today and tomorrow. So as you are aware, fruits that are commonly ripened are bananas, probably the number one ripened fruit in the United States. We get tomatoes, avocados, pears, mangoes, and in the case of citrus, like and you'll hear from Mary Lou for purpose of degreening. And how do we optimize ripening or degreening? There's many factors that influence this, and each of them can somehow be controlled to a certain point. So first of all, we have fruit temperature, which is really important, and it's probably one of the most important factors to control during ripening. And each fruit is receptive to the presence of ethylene or ripening regimens if the temperature is optimum for ripening conditions. Room humidity as well, probably not as crucial as temperature, but it's also important. Carbon dioxide, mainly keeping the levels of carbon dioxide below an acceptable level to avoid any quality issues like fermenting flavors or aromas in the produce, which varies also from produce to produce. But generally speaking, keeping the carbon dioxide before a specific level. Ethylene gas, which as you've learned or will learn, it's the hormone of ripening. Airflow rate, to keep the movement or expose the fruit to ethylene, temperature conditions, and also remove the carbon dioxide that is present in the room. And last, it's probably also really important is how do we monitor ripening? It's not as easy, it's not as trivial as we think, and I'll talk a little bit about it in detail and what are our thoughts of what can be done in the future to better monitor ripening. So let's start a little bit with the room design, and I'll talk about what are the conditions of airflow, ethylene, and everything later on. But right now, in the initial part of my talk, I would like to talk about what is the room design. And here we have the first type, which we call conventional room and degreening, which is fairly inexpensive. It's just basically an open room where we have a fan that is distributing the air through, here's probably an air damper that redirects the air and forces that air through, or somehow forces that air through the pallets. This is a typical setting for citrus degreening. There's other conventional settings where there's more air spaces to allow higher airflow. But basically the take-home message is that this is fairly simple, it's inexpensive, it's adaptive and easy to use. You can use any storage facility to ripen your fruits in this case. The problem is that, and you can imagine that in some cases, some of the pallets might be exposed to higher levels of ethylene, and the air distribution is probably not as uniform. Therefore, you get low uniformity of ripening, but generally speaking, even though there's low uniformity of ripening, you typically achieve a good, and it's enough for degreening of citrus plants. So this type of conventional room is typically used for citrus degreening. And of course, it's an open space, and there's significant losses of not only space but energy, higher energy consumption, and so on. So this conventional room or ripening or degreening facilities, even though they're applicable and you can use them, they're probably not the best, and therefore the industry has designed other type of systems that are more not only energy efficient but also much more efficient in distributing that airflow and that ethylene through the produce itself. And here we have an example. Similarly to, if you're familiarized to forced air cooling, this is forced air tarp ripening systems, where we have a set of fans that are typically forcing that ambient air with ethylene, temperature and so on through the pallets of produce. This can be installed in any storage or facility, only that if we compare it with the conventional system, it's slightly more expensive. In some cases, you can make it portable and flexible, as this example right here. You could, probably install, a set of movable tires that you can move this system to force the air through the produce. You can also adapt it to small and large pallet sizes. And there's really no need of vertically stacking the pallets like in the previous slide of conventional type ripening. Here's some that are slightly more advanced, where we have large forced air tarp-free ripening systems. So as you could see in this picture here, to force the air through the produce, we install a tarp, and just basically the air can't go anywhere else except through the produce. But there's also designs where we do not need to use tarps, and this is typically for larger facilities, heavily used in many banana ripening facilities. It's the most uniform in temperature and ripening conditions, the much more advanced. Here I just set up an example, some airbag system which somehow acts as the tarp, and it redirects the air through the produce itself. It's easy to access, less labor intense. You could use forklifts and so on to handle the pallets. It allows a two-way airflow with reversing fans. Typically, the previous slide, the forced air, even the smaller facilities, you can also achieve that. And basically, this allows you to have a much more uniform ripening. As you can imagine, if we look at this picture here, if we turn the fans around or the flow around, and we can allow air to go from the inside out instead of from the outside in, that would be advantageous. As in this case, both temperature and ripening would potentially, or temperature conditions and ripening would start from the outside in. And this larger systems can also, you can also incorporate variable speed fans, which increase the efficiency of your system. And I'll talk a little bit more about this and how this is achieved in my talk tomorrow. And last but not least, there's also certain companies like this company, Millennium Cooling. I believe this company is in Florida, if I'm not mistaken, but Millennium Cooling has designed a system, there is a transit ripening and cooling system, and I use the word cooling here. Really, it's probably not the best word, because in many cases, this system does not allow you to effectively cool the fruit, but they've been successful in redistributing the ethylene and the ripening conditions to better ripen the fruits. And it's just basically as you're transporting the commodity that it can be ripening. When it comes to the room design, very important, you need to keep, as I've said, the optimum conditions for ripening. And one is relatively high relative humidity. And by that I mean typically, and it's specific to every commodity, but typically ripening conditions of relative humidity need to be like between 85 or 95% relative humidity. And in the dry conditions of California, for example, this is not easy to achieve if you have not designed the room correctly. And this is what you need when you're initially designing the room. It's not just any room. You need to have a good insulation that keeps that water vapor inside our room. and the fluctuations of climate do not affect the conditions of our room, basically. This is some typical temperatures, and bear in mind that this may vary from variety to variety, and what I would encourage you to do is to look at the produce facts of each produce that you're ripening, and to find the right conditions of ripening, not only of temperature management, but also ethylene levels and so on. But this is just some examples that I've put here regarding the conditions of the room. So we get, for example, tomatoes need to be ripened between 70 to 75 Fahrenheit, while in the case of avocados, that might be a little bit lower, and so on. This is just a graph, a typical example of ripening, a typical banana ripening profile. Here in the y-axis, we have temperature in Fahrenheit and in Celsius in ripening days, and we have two different regimens, or two different profiles. One is a 4-day cycle, and another is a 7-day cycle, and how the temperature is managed through that ripening. As you can see, if we want to accelerate the ripening, in this case of bananas, we need to have higher temperatures. But regardless of that, to keep the banana, in good quality, once it's ripened, it's expected for us to reduce the temperature to storage conditions. It's not really stopping the ripening, but it's slowing it down significantly. As I've said in the beginning, if the CO2 levels in the case of bananas gets above 1%, that might affect the quality of the produce. Therefore, in any case where we're ripening, we need to vent the air as CO2 increases significantly. And I'll give you some rule of thumbs basically on how to keep this, but generally speaking, we need to keep it below 1 or 0.5 to 1% or lower than that, the levels of CO2. As you can see here, this bar indicates the time required to inject ethylene, C2H4, and the concentrations of ethylene in this case vary from commodity to commodity as well. And last but not least, as I've said, temperature management is extremely important. If we look at the regimens of drying for bananas, they need to be kept between 58 to 65 degrees when they're being ripened. And we cannot allow the bananas to go below 13 degrees Celsius, 10 degrees Celsius, typically 50 to 55 Fahrenheit, as we can have any additional quality issues. But we have these probes, orange probes. Those are thermocouples that are set in the ripening rooms in the fruit itself to monitor the temperature conditions of the fruit. We can record this in many cases now. You have touch screen and like the world is the limit, and it's an ongoing changing science. Ripening monitoring, and this is an ongoing science even for engineers. I am currently in conversations with at least 2 or 3 different companies, and their question at the end of the day is, how can we monitor ripening so that we can reduce labor? And that's probably the number one concern. They get their ripening experts, and how they, in the case of bananas, what I've heard is that they open the banana and they check the translucency of the banana. And that for me, it's almost like a foreign language. Like, what is a translucency? How can you explain this? How can we monitor this automatically? It's been said, and we are aware of this, specifically for bananas, if we continue with this example, that color changes are typically not related to ripening. In many cases, you can get a banana that is greener, that is not as sweet as one that is a little bit more yellow. It doesn't relate completely. That being said, there have been some efforts like this probe, which was developed in the department where I am, Department of Biological and Ag Engineering, If you're interested in learning more about this probe, it's an inexpensive probe that was developed, I think it was probably like 7 years ago, by Professor David Slaughter and my predecessor Jim Thompson, where they have a wireless probe that connects to the banana itself and can monitor how the color changes in the banana, and it somehow relates to maturity. As these techniques evolve, as the sensing technologies evolve as well, we have the expectation that this could get smaller, much more inexpensive, and so on. But that being said, because we are aware that color is not the only factor to measure ripening, we need to find alternative means of measuring this and relating this with sensing equipment. I'm in conversations with a company called C2 Sense. They develop probes to sense different gases in the air. It includes ethylene, CO2, and others. So if we can somehow find a relationship between ethylene levels, for example, color, and other factors to monitor ripening non-invasively, it's ideal. And basically, the take-home message is that we are looking into that as it's a need of the industry currently. Firmness is another method. Typically, firmness is it's a means of monitoring ripening. That's what I mean. The disadvantage of firmness is that it is typically an invasive measurement, which requires a destruction of the sample. As we can see in this graph, in the y-axis, we have firmness in pounds measured from pears after certain hours of ripening. And we can see how the firmness significantly reduces as the as the pear is ripening. Here we have some examples. This is a FirmTech. This is non-invasive means of measuring firmness. They are available for larger fruits. I just have this one as an example. But there's others, of course, much more simplistic methods that allow you to monitor how firmness changes over time. And specifically, based on what I know, I think that firmness relates much closer to ripening than color actually does. Sonic and ultrasonic vibrations. I've been mentioning this word non-destructive or destructive. In this case, this technique is non-destructive. It's a means of assessing firmness. We have here an example where we have a graph. On the y-axis, we have the relative deceleration of this spherical impact tip. We had an accelerometer that is recording. So, long story short, what this does is what, basically my grandma would do in the store when she would grab a melon and just start banging on it and hearing it and everything. I mean, I do it in the store just because I want to be cool, but I don't know how to do it. But basically, there's physics behind it, and the physics behind it is as I said here in the example, the relative deceleration of this probe in a soft pear is lower in comparison than one with a firm pear, and it makes sense. And we can measure this mechanically. It relates well, generally speaking, with this impact firmness score relates well with the firmness of the produce. And it also relates well with invasive methods like this penetrometer firmness. Basically, this is comparing this impact firmness score, non-invasive, non-destructive, with an invasive method of measuring firmness. At the beginning of my talk, I said I was going to talk a little bit more about airflow and how it moved. I'm just basically a zoom in of what I initially talked. We get here the airflow in the conventional method. You have an air conditioning coils. It's a fancy way of saying refrigeration system, and fans that can distribute the air deflectors that can deflect the air through where we want that air to go through the produce and so on. This is typically how a forced air ripening room looks, regardless if it's tarped or untarped. Airflow citrus or degreening, similarly to my first picture that I have there. And airflow rates, as I said, vary from commodity. Generally speaking, in the case of avocados and bananas, we have around 0.3 CFM per pound of produce. This might be a little bit larger in avocados, and generally speaking, it's because avocados produce probably around almost 3 times more heat than banana, and therefore they require a higher flow of air. And in the case of degreening, it's a much lower airflows as the ones that I've expressed here. Ripening room relative humidity. I briefly touched through this, and I mean it's simple. Actually, it's not as simple. It's simpler to handle or control temperature than it is to control relative humidity, but it's still necessary. So in many cases, the ripening rooms contain humidifiers that can add waters or water that the particle of water is small enough with small energy so that it's almost a fog. It looks like a fog, and it does not wet the environment. It dissipates and it directly goes into the airstream, and therefore you get a significant increase in the humidity. If this is not designed appropriately, and if it's not handled appropriately, it could bring additional problems. High levels of relative humidity, especially in a cold room, you can get condensing, and then the corrugated boxes might be affected. Other issues of disease and so on. So relative humidity management and handling is very, very important. And as I've said, it's somehow trivial to handle temperature, but relative humidity, it's still evolving. Even systems to the day of till now. If you do a literature review, you're going to find that there's newer systems that haven't even been incorporated in ripening rooms, like it's ultrasonic type humidifiers and so on. So this could also evolve. And of course, there's automatic relative humidity controllers that control the nozzles and the input of air and so on to better control relative humidity. But it's also an important factor that needs to be considered. And here I just have a picture of a psychrometer. Back in the days when we didn't have digital relative humidity probes, typically this is how we could infer what was the relative humidity in the room. And I won't go in detail much into this because it's not the purpose of my talk, but it's psychrometer or psychrometry, which is basically the thermodynamic properties of air or the properties of moist air. It allows you to basically control that relative humidity, avoid condensing, and control it based on specific temperatures and so on. And so if you're interested in knowing a little bit more about this, I'll encourage you to go look into psychrometry. As an engineer, the psychrometric chart it's a day-to-day thing that we do, regardless if it's refrigeration, drying, the designs of the system. Psychrometry and understanding psychrometry is very important. And last but not least, ethylene management. This is, of course, without ethylene, we are not going to have an optimized ripening. Typically, for ripening, we have concentrations between 100 up to 150 ppm of ethylene, but it has also been demonstrated that usually it's effective below 100 ppm. In some cases where we get this automatic ethylene control systems, like the one that I've exemplified here, much lower concentrations in ethylene can effectively ripen the produce. And for degreening, the levels are significantly lower than ripening. There's many ethylene sources that are commercially available. Let's start with gas from cylinders, where you inject the ethylene, as I've described in this sketch right here. And you can control the volume or the injection quite accurately. You have catalytic generators, as the picture here, centralized ripening systems, which are also generating ethylene. Ethaphon, which is also used in many cases in the field. Ripening fruits, believe it or not, if you do not have other sources of ethylene, let's say in a developing country or something where you want to ripen something like relatively small scale, ripening fruits generate significant amount of ethylenes, which is also something that you need to be aware. If you do not have your facilities properly maintained, and there's ripening fruit in that same facility, even with produce that could potentially be ethylene susceptible, you're going to have problems. Welding, smoke, cigarettes, exhaust from internal combustion engines, like if you have a propane forklift and you want to control ethylene levels, this can generate quite a significant amount of ethylene, an uncontrolled amount of ethylene. So again, it's not only sources to ripen, but also caution when you have a ripening room. It's best to have electrical forklifts instead of propane forklifts, for example, and so on, to avoid uncontrolled levels of ethylene. Right? Also, really important is ethylene safety. So ethylene is it's explosive, so it at very high concentrations, much higher than the concentrations that you're dealing in the ethylene rooms. But still, my recommendation is that you need to follow the manufacturer recommendations, especially the labels. I have not, in refrigeration and so on, ammonia is much more of a concern, if you ask me. But we also need to be cautious. And basically, you need to measure and monitor the ethylene and avoid for it to going above 2,800, which is, as you know, based on the regimens of ethylene and what you've learned so far, is much, much higher than you should actually have in that room. A rule of thumb, as I mentioned, 6 to 8 room air exchanges drop ethylene to 1% of original level. So, and again, this is a rule of thumb. The same happens with CO2. And again, this is measure and monitoring ethylene above this level, but ethylene is combustible at extremely high concentrations. It's like around 28,000 parts per million, where ethylene is combustible. So it's even much higher than the recommendation that we have here. But it's just a kind of a safety concern. Keep your eyes open. And again, how do we keep this safe? Continuous ventilated systems, small fans that can remove that ethylene from the rumen or the CO2. We also have ethylene sensors. This is just one example. Tomorrow I'll talk a little bit more of other ethylene sensors. But this global cooling ethylene sensor has a 2% accuracy rate, and it monitors. They have 2 different models. I believe they have a third one now, but to efficiently monitor the ethylene concentration from 0 up to 100 parts per million. And there's others, of course, other manufacturers. This is just one example. You mentioned mixed loads here. Here we have some examples where ethylene could be problematic. After, in this case, flowers, if you expose them to 2 parts per million of ethylene, after 3 days, they've dropped all their petals, pretty much, and we don't want that. 5 parts per million, which is around the concentrations that you're doing for degreening of citrus, fairly low. You get this effect in quality in the watermelon, and kiwis are also highly susceptible, even at parts per billion concentrations, much, much lower. it induces softening, and it's highly susceptible. So, you know, if you have these highly susceptible fruits, don't mix them with fruits that produce ethylene. Carbon dioxide, initially in that banana regimen that I showed at the beginning, I mentioned 1%, but typically CO2 has to be less than 0.5% in that room. And thanks. And again, we achieve this through ventilation, and I'll leave this here as my time is almost over. But you know, similar to ethylene, you achieve this through ventilation. There's of course CO2 sensors. The world's the limit, and there's many manufacturers out there that produce high quality sensors for CO2. And with that, thank you very much. And I guess I don't know if I have time for questions.